they're the same matrix. So these rules are sound. Like they're not going to steer you awry. Steer you awry?
Right.
Awry. Okay. Yeah.
So the soundness is defined explicitly with respect to this functor from SFGs to matrices.
Yep.
Or maybe soundness with respect to arbitrary functors out of SFGs.
If I use some weird one where like I did 3-1 or whatever I did before, that would not satisfy many of these rules. Did I answer your question?
Yeah, I mean, I'm saying, so we have port graphs and we have functors out of free props. So can we be sound with respect to some other functor? Or is it just soundness with respect to this particular functor?
I see. I think what I meant to say is that SFG to MAT, SFG to mod 17 equations. What am I trying to say? You're trying to find the right way to use the word sound in a sentence, kind of?
So like I'm asking, is sound a more general thing that we're interested in, or is it just about this particular functor?
It's some proof techniques you give yourself, or some rules for deduction. Are sound, in some semantics, means that if you can deduce something using your rules, then that thing is true.
Okay, so it's about general functors from syntax to semantics.
The term sound. But in particular, these equations are sound for
yeah,
the category
these equations are sound for the
particular functor.
matrix functor.
Right.
Okay, great. Everyone good? They're also complete. The fact that the functor exists means it is sound. And the fact that it's an isomorphism means they're complete, which says any time two matrices are equal, two signal flow graphs give same matrix, you can get from one to the other. Using these rules. So you could take any two signal flow graphs, as weird as they are, and they give you the same matrix. There's some series of using these 17 weird pictures to move them around until you get that proof. You get the proof that they're equal. There's always a proof when two things are equal. Okay, so that's what we kind of, in the beginning I said, props, presentations, and proofs. And this is what I meant by the proof part, is that these rewrite rules give you proofs that two matrices are the same, and anytime they're the same, you can prove it. Yeah. Did you have a question?
Can you generate this?
I'm not going to ask you, of course, to do it all out right now, but how do you prove in general that, like, for instance, that these 17 equations are all unique? Like, that
I didn't do it.
right, I know. I'm asking you.
Yeah,
normal form
I don't
for the
know how.
diagrams.
Yeah,
Are you
probably
familiar
normal
with
form.
normal forms? The idea of a normal form?
Yeah,
So there is so you can characterize the pre-image of any matrix in a certain way, and you show that anything in this pre-image reduces to a normal form, and you can show that because you can reduce any diagram to its normal form using these rules, you can prove the quality of any two diagrams that represent the same matrix.
How do you get to the 17 rules in the first place then?
Who gives them?
Someone other than just like...
So
Yeah,
these are actually familiar structures. So the top one you can see sort of expresses something like associativity.
Right. This one's associativity. This one is a unitality.
But like more general than just thinking really hard
No.
for a long time.
I think it's thinking. Well, I guess it's like in category theory we have things that we see a lot, and you write down the things that you see a lot, and then you think, are there any more? And I think there maybe you ask. You have to work really hard. Is there any working really hard that goes on, or
There are
is it
some
all
more
obvious?
procedural things you can do, like using distributive laws. But in this case, it's a simple enough case that, and matrices are well known enough that you would probably just do it by hand.
Right, so this one says addition is associative. This one says adding the unit is doing nothing. And this one says A plus B equals B plus A. And so since you expect all those things from matrices, you write them down in this format. But I don't think I would have found this one if I hadn't already seen other people write it down.
But that is also a well-known
It is
law.
a well-known-
It's called the bimonoidal bialgebra law, and if you've seen certain things like bimonoids and bialgebras in algebraic geometry, that's precisely the right way to talk about how they work.
I agree. Okay, so any other questions? Did you have a question?
No, I was dabbing.
Dabbing? What is that? I don't know what that is. I'll look it up afterwards. Dabbing. Okay, so from matrices to behaviors. So the last part, I haven't been writing this down, writing my outline, but let's move from matrices to behaviors. So in the last class, the 7th class, we'll be talking about very general sorts of behaviors, like kind of any kind of behavior you can imagine. I really think literally any kind of behavior you can imagine will fit in that framework. Like the behavior of a person who's in love or something, like that kind of. But you would, not that I know how to write that behavior down, but that you could, that's the kind of thing we'll be talking about in the last one is like very general behaviors, meaning what a person who's like that will do, I guess.
So
Yes.
the behaviors are not math things?
They're going to be math things,
Okay.
but any kind of thing you can imagine, you would be able to conceptualize as one of these sorts of things. That's the claim, we'll see. Hopefully Brendan will be able to support that claim.
Oh no.
But, or fail to do so.
Dave
but
is leaving
today-
the country and
I'll be
building
in the
up.
country, so I'll be. Okay, so today we are talking about a very, very specific kind of behavior, which is the behavior of. So in this box, instead of matrices like y equals mx. So here I have like y is in R3, and x is in R4. And we've talked about this kind of thing. That's you could say that's a behavior. The behavior is that y will always do m times x. The signal coming out here will always be that. But in general, I could say ny equals mx. So that I say this guy is satisfying its behavior if the inputs and the outputs satisfy this relation. So the set of all x, y such that ny equals mx. I'd label my box like that. So it's some kind of linear relation between two vector spaces, two Rn's. So a behavior, so I guess we could call this like a linear behavior. Behavior of type Mn is a subspace okay. So we're saying here that every time we were drawing a box like that, that'll count as a behavior. The behavior for this is that this will be the sum of those two. The out will be the sum of the ins. But now we're doing much more general things. And so so it turns out that all behaviors of this sort, all such linear behaviors, this is the only kind of linear behavior I mean. All linear behaviors are can be represented by signal flow graphs plus their reverses. By which I mean, if you're allowed to draw these pictures like before, but you're also allowed to draw these pictures. So I reverse the direction that dot was allowed to go. And I reverse the direction that the circle is allowed to go. And I reverse the direction that that guy's allowed to go, etc. So now everything can go in either direction. Then you can get all linear relations this way.
So what does the reverse of the adder.
Yeah, let's try to figure out what these different things mean. Okay, so what is the reverse of these different things? What do they mean in terms of relations? So I already know what these mean, but what does this one mean? So this one means that x has to go with xx. What does this one mean?
Has to go with X.
Xx has to go with x. It just means all three of these have to have the same value. So if you ever see a black dot, everything on it has the same value. They're all the same. So what relation is it?
Does that mean
It's a
if
set
you-
of all x, comma y, comma z in R2 times R1, because that's what I said it had to be, the form it had to be. Right, so it's all x, y, comma z, such that x equals y equals z. Okay. Any questions on that? Okay, so we already said this thing is like some kind of weird 0 by 1 matrix. What is this one as a linear relation? It's a subset of what, first of all? Subset of all x in R, such that
That.
nothing, no rules. Because what this took, it took any x and just killed that information. Now we're starting with no information, any x is legal. Okay, so what about, this one was, this one produced 0. What should this one be?
0.
X equals 0, yeah. Okay, this guy, x, y, z. This was like x plus y equals z. Now, z equals x plus y. So they just reverse. Okay. The neat thing about this is that this forms a compact closed category, which we talked about a couple times ago, or maybe last time. So is this okay? Are you guys good?
I just don't see it as being deterministic. In what
It's
comes
not
out.
deterministic, it's a relation.
Okay.
So relations are kind of possibilistic instead of probabilistic or deterministic,
Okay.
which means given an input, there's a set of possible outputs.
Okay.
In this one, given an input, the set of possible outputs is either that value or nothing. So if it's the same value here, it'll output that value. If it's a different value, it'll say that's not a possibility here. There's no way that could have happened, something like that. So if you have some circuit and you've got some wires here and you've got electricity flowing on them, then if these two are different amounts of
Potential.
You get a short circuit?
Potential.
yeah, then it's not the circuit is not living as a circuit anymore. Right. But if they have the same value, then this one has the same value too. Okay. So if I take this, which means anything's possible, and then I split it, what are the possible values in R2?
Anything equal to 10.
Yep. Great. And this one also is just all XX. And so you can use these to form what are called the cups and caps for a compact monoidal, compact closed category. And what that means is you have some things coming in, you're allowed to split them, you're allowed to say that this one is the sum of these two, you're allowed to do whatever you want. But you could also take these two things and cap it off like that, which in some sense forces this to equal that, right? It forces this value to equal that value. And so the way we have been drawing that is just like that. So you can curve these wires around because what this picture right here actually means is a black dot with another black dot. I mean, in both cases, it goes from a two-dimensional thing to a zero-dimensional thing. Whether I draw it like that or like that, it's just kind of shorthand. Just like before we were drawing that picture and said, like, why waste our time with that? Why not just forget this box and draw the pretty nice looking picture? So in the same way, we get what's called a compact closed category, which means we can turn wires around. We get feedback as a legal thing by using these guys to do it. Yeah.
Is this thing a compact closed category yet? Because I think we said that we wanted the relations like the S shape and the Z shape to be equal in a.
Right. So if you took this guy and then this guy, you would want that. Why did I? Wait. You'd want that to equal this guy. So if you check out what the matrix will, or the relation will do, it'll take an x, it'll force it to be the same as this x, it'll be forced to be the same as this x, which is the same thing that this relation
So I
does.
see that that's true in the category of linear relations.
Yeah.
But not in the signal flow graph, which is just a free category on these.
Oh, that's right. That's right. That's right. Yeah. That's right. Okay, so we have about 3 or 4, well, 5 minutes left, I guess. But using these diagrams and using what's known as Laplace transforms, which means you can turn, so if you have something like x double dot equals x plus 3y dot, there's something called the Laplace transform that makes these dots, the derivative with respect to t, into just multiplication by something called d, let's call it. So d dot x equals x plus 3 dy. And d is the opposite of s, where s stands for the integral. And so using these kinds of things, you can write down, so in signal flow diagrams that are actually used in control theory, they're doing the same sorts of things we are, where you have numbers in these things, but instead of numbers, you have numbers and elements of d, like d's and s's. So you write down pictures like I did in the very beginning, where you say like the force we're going to take, the amount of acceleration I want, or the amount of force I want. Let's say, yeah, force. I'm going to divide that by the mass. That'll give me the acceleration. I'm going to integrate that, and then I'm going to take that and the intended velocity, and I'm going to add them, and that's the velocity. So I don't know if this is the right diagram, but you can make some kind of feedback. A real control theory person would be able to take these ideas and create a diagram that says, based on the velocity I want and the velocity that I have, and the force that I need to apply to my car, and whether I'm going downhill, etc., I'm going to make a feedback loop that will force my car to continually try to return to the desired velocity. And they'd write these diagrams in this kind of language and can reason about them in this kind of language with the same rules we can about turning one shape into another shape. And yes.
So for the real control theorist, so those diagrams is nothing about how to actually implement feedback.
Right.
It just says what you want.
That's right. And they have rules that tell them how they can so they can solve for those. So there's some kind of, they may say, I need to do ax times by to get you this. And they can do some manipulations and kind of use those to help them figure that out, to figure out what a and b should be. Other questions? Yeah.
Is there anything that, like having this perspective bias for that,